Next up is Mr. Peter Cartwright. Peter entered the water purification and wastewater treatment industry in 1974, and he's had his own consulting engineering firm since 1980. He has a degree in chemical engineering from the University of Minnesota. He's a registered professional engineer in that state. Peter has provided consulting services to more than 250 clients globally. He has authored approximately 200 articles, written several book chapters, presented more than 160 lectures and conferences around the world, and is the recipient of several patents. He also provides extensive expert witness testimony and technology training courses. Peter is a recipient of both the Award of Merit and Lifetime Member Award from the Water Quality Association and is the technical consultant for the Canadian Water Quality Association. Please welcome Peter Cartwright.
Thank you, Bob. What I'd like to talk about is treatment technologies. I'm a treatment guy, and I've learned a lot in the last 2 days about where we're going, sustainability issues, and this sort of thing. But as we all know, once we collect water, once we isolate various sources of water, we have to treat it. And so what I want to talk about, and I will apologize in advance if I take a little bit more than the time that has been left for me, but I'll try to go rapidly. When I give these lectures, I always write a paper, and I do have about a 44-page paper that you can get from the IATMO website. But if anybody would like to have me send a copy to them, just give me your card afterwards. I'll be around the rest of the day. But what I want to talk about is what's in the water that we want to remove. Obviously, when we talk about potable applications or high purity applications, that involves taking this wonderful material, water, and removing contaminants from it. And I basically want to talk about the general technologies. We talk about filtration and get specific with membranes. I'm a membrane guy in my own experience. And then wrap it up with disinfection. Now, I won't spend time talking about the issues. We've heard them from numerous speakers in the last day and a half. So I'll just move into what are the contaminants. And to simplify the discussion of treatment technologies, we kind of have to break the contaminants down into 5 classes. Suspended solids, dissolved organic contaminants, dissolved inorganic or ionic contaminants, microorganisms, and gases. And gases will get very little attention by me because they're not really an issue unless you're in an anaerobic digestion environment where you've got sulfate-reducing bacteria producing hydrogen sulfide, or you've got methane or something like that. But generally, the removal of gases as contaminants is not nearly as important in general as the other classes. Now, I think the important thing, just as Bob Boulware said in his lecture just ahead of me, you can't remove all microorganisms. You can't remove all of anything from water. And we heard a little bit about that yesterday, the PCPP issue, the fact that because we can now measure down into the part per trillion concentration of contaminants, we're also identifying the fact that our water has a lot of different contaminants in it. They're just extremely small in quantity. So let's talk about the filtration technologies. We have conventional filtration, cross-flow pressure-driven membrane technology, and then as a technology, certainly not a filtration technology, I want to address disinfection. This is kind of a summary of the treatment technologies that are used for industrial water treatment. We have a huge plethora of technologies that have been developed over the years, so there's no shortage of treatment processes available to remove contaminants from water. But what I want to concentrate on are the ones that are most easily described and most commonly used. Bed filter, media filter. This is basically using something like sand or another material to filter large suspended solids out of the water. Then, and we heard a little bit about that yesterday, slow sand filtration, rapid sand filtration, et cetera. Cartridge filters, they've been around for quite a few years now, 50 or 60 years. They basically do the same job as bed filters. However, they're a little bit more convenient. They're really designed for smaller volumes. Bob Boulware mentioned rainwater harvesting. Obviously, at least in a residential application, cartridge filters would probably be the best technology for removing the suspended solids. You can get these down into much finer, higher quality cartridges that'll remove even into the submicron range. You can't get that with bed filters. Bag filter is kind of a hybrid of a cartridge filter. It treats larger volumes. It's not as versatile as a cartridge filter. You can't get it down to the small pore sizes, but it's used very commonly, primarily in industry, where you're dealing with generally higher flow rates. The materials of construction, primarily in the cartridge filters, as you can see, are extremely varied. You can get cartridge filters made out of just about anything, including ceramics, and a whole different section. We won't spend much time on it today, but the paper goes into it in more detail, and that is activated carbon. It doesn't use filtration technology, at least the normal granular activated carbon. It uses adsorption, but it's an extremely versatile and important filter material, particularly for removing low molecular weight organic compounds from water supplies. And continuous filters, these are filters that are automatic backwashing, more applied to industrial applications, where you have, let's say, 100, 50, maybe 50 micron, relatively large particles, and these continuous filters will automatically backwash. They're quite expensive, but they have rather low maintenance requirements. And now membrane technologies. And the reason that they have become so important is because they're so versatile. These are basically cross-flow pressure-driven membrane technologies. There are 4 classes of those: microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. And when I first got in the industry in 1974, the primary membrane technology was reverse osmosis, and it had a bad name because it had been sold by people that wanted to make a quick buck, and they would put in an RO system into a facility, and they would say, just turn it on and walk away, you never have to maintain it. Well, we've learned a lot in the last 50 years about maintaining these systems. There's no perfect system. They all require some sort of attention. The conventional filtration, bed filters, cartridge filters, et cetera, these are all involve one stream that goes through a filtration medium, and hopefully everything you want removed is left behind, either on the surface or down inside the medium. With cross-flow filtration, you involve one stream coming in, but you have 2 streams leaving. One stream is the stream that passes through. It's permeated through the membrane and is called permeate. The other stream, containing hopefully all of the contaminants you want removed, continuously leaves that stream in a cross-flow parallel path and that is called the concentrate, the reject, the brine. One of our problems in our industry is we have too many synonymous terms. I actually have written a kind of a glossary of terms just for the membrane industry, because it can get confusing, particularly with a new technology that you may not be knowledgeable about. Cross-flow, pressure-driven membrane technologies have a number of particular advantages. They're continuous as opposed to a batch process. They're capable of removing contaminants down into the submicron size range, even into the ionic range. They usually require no chemical addition. They can be backwashed if they're microfiltration or ultrafiltration membranes. Generally, they're run in turbulent flow conditions to minimize fouling, and they usually have a relatively small footprint. Microfiltration involves basically the removal of suspended solids. There are different definitions by different membrologists, but my definition of microfiltration is the removal of suspended solids. Here's the membrane, water goes through, salts or ionic materials go through, dissolved organic materials pass through, but the suspended solids are held back. Ultrafiltration involves a tighter pore size. It not only holds back suspended solids, but it holds back the dissolved organics. The definition I use for ultrafiltration is the removal of dissolved non-ionic contaminants. Both of these technologies work on a sieving basis. What's too big to go through the pore ain't going to go through. It's as simple as that. Nanofiltration is a kind of reverse osmosis. It's a loose reverse osmosis technology. It involves the removal of multivalent salts. I apologize if I'm getting too far into the chemistry of it, but basically dissolved salts are either monovalent, only one charge, or multivalent, more than one charge. Calcium, for example, is divalent. Magnesium is divalent. Sulfate ion is divalent. Aluminum is trivalent. These salts, multivalent salts, are rejected to a higher degree in nanofiltration than reverse osmosis. Why do we use nanofiltration? Because it's a lower energy process. So if you don't need a really high quality of water from an ionic standpoint, nanofiltration would be a less expensive approach. And then reverse osmosis, the ultimate. There are membrane technologies. I just read about a new manufacturer on the market that now is advertising 99.85% rejection of sodium chloride. So it ain't 100%. It will never be 100%, but it's awfully, awfully good. You cannot make 18 megohm quality water with reverse osmosis on a practical basis. You would need to use that as the preliminary treatment, followed by some polishing technologies such as CDI or electrodeionization or one of those. But it has become the workhorse. If you have to remove dissolved salts from water for any application, reverse osmosis is usually the choice. This is a chart, and unless you have the paper in front of you, it's much too complicated, but it just compares the various parameters of these technologies with as compared to the microfiltration, ultrafiltration, nanofiltration, and reverse osmosis, how they differ from each other. This is the other half of that chart. So this is kind of a summary slide. If you want to remove suspended solids, the choice is microfiltration. Ultrafiltration removes suspended solids and the dissolved organics. Nanofiltration removes the above plus the multivalent salts, and then reverse osmosis is the ultimate in these cross-flow, pressure-driven membrane technologies. And once you've identified the technology you want to use and maybe selected the polymer, now you have to identify the device that is best. The four classes here, plate and frame, tubular, hollow or capillary fiber, and spiral wound, are the general classifications of the way these membrane devices are packaged. Spiral is the one that if you think of RO, you virtually always think of spiral. And that is the one that is the most interchangeable. Today, there are about 7 manufacturers of spiral wound membranes in the United States. We have a monopoly on that right now because they were invented in the late 50s in the US. And virtually every one of these membrane devices, spiral devices, can be interchanged with everybody else's. So it's extremely competitive business. And the bottom line is, if you need to use reverse osmosis, although you can get an RO membrane in plate and frame or in tubular construction, it is not going to compete with spiral. So it is a very, very competitive business. When the 8-inch diameter spiral membranes first came out, they were over $1,000. Now those same membranes are in the $300 to $400 range, simply because of the competition. Plate and frame is basically like a heat exchanger or a filter press. You have the feed water going in between the layers of membrane, and under pressure, all this area in here is pressurized. Under pressure, the permeate goes through the membrane and is collected as permeate, and those are the yellow lines coming out. Tubular basically is like a pipe with a membrane on the internal surface. It is basically made out of a porous material so that once the permeate passes through the membrane, it exits through the wall of the pipe. This is another illustration of it. The hollow fiber is basically, it's a small tube, but it's very small diameter, normally in the millimeter diameter range. These are made differently than the other three. They're made by extruding a fiber of the polymer that does the rejecting or the removal, and there is no support layer. They're unsupported polymers. And here's another illustration of that. And then the spiral, which is unless you've actually read rather thoroughly about spiral membranes or taken one apart, it's a little hard to envision how it works. But it's basically a double layer of membrane-coated backing material that is sealed on 4 sides, so that the only way water can go through the membrane is to go through the surface, and then it's collected and wicks around in a spiral fashion and comes out through the permeate tube. Basically, the reason we've got these 4 different configurations is because they all have pros and cons. And the 2 parameters that are used to measure them are, 1, packing density, how much area, membrane area, can you get into a given volume of device, and the fouling resistance. And these are basically inversely related. The tighter the packing density, the less the spacing between the layers of membrane, and the more likely it is to foul. But generally, the packing density is related to the cost of the per gallon produced. And so the higher the packing density, the lower the cost, but the most susceptible to fouling. And fouling is the primary, it is the cause of membrane failure, almost without doubt. Yes, you can have chlorine attack or something like that, but 99% of all membrane failures are due to fouling. So fouling means that all of these contaminants that you wanted to be removed are not all removed. Some of them are left on the surface. The Microfiltration and ultrafiltration membranes have a significant advantage over the nano and reverse osmosis units or membranes because as I said earlier, virtually 100% of all reverse osmosis and nanofiltration membranes are in spiral configuration, and they cannot be backwashed. Because they can't be backwashed, you've lost a tremendous maintenance advantage. The microfiltration and ultrafiltration membranes, as you can see there on the slide, they're available in a lot of polymeric configurations or polymeric constructions, and you can get them in a number of non-polymeric or inorganic constructions. They can all be backwashed. This slide is particularly important because you can see the spiral wound. You can get spiral wound membranes with a number of these different polymers, but they cannot be backwashed. And this is a slide just devoted to the NF and RO membranes, what they're made out of. And as you can see, there are no RO and NF membranes that are available in non-polymeric configurations, materials. They've been working on them for years, but to date, there is no membrane that has a salt-rejecting capability that is made out of anything other than these particular polymers. What's called the TF on that chart is thin film, and CA is cellulose acetate. Those are the only two commercially available polymers that will reject salts. Interestingly enough, there's a lack of agreement among the experts in the field as to how reverse osmosis membrane rejects salts. Nobody really knows, or at least there isn't universal agreement as to what the mechanism is. We know it works, but exactly how salts are rejected from the membrane surface is still not fully understood. The PS, polysulfone, and PES, polyether sulfone, these are common polymers used for ultrafiltration and microfiltration membranes. They're also the underlayment on which this thin film composite is deposited. So fouling, as I said, that's the bane of all membrane technologies. This slide kind of illustrates a membrane and what it might be seen microscopically in the way of contaminants which may or may not foul the surface. And I don't have time to get into all the mechanisms of fouling. The paper does go into that in detail. But basically, you can have fouling from suspended solids, dirt, etc., precipitated salts. These are the slightly soluble ionic components like calcium carbonate, barium sulfate, calcium sulfate. Some of these materials that are slightly soluble, once they are concentrated by the membrane process, they will tend to become insoluble and may scale the surface. Microorganisms, biofouling, that's a whole study in itself and a very complicated issue. And organics, oily materials, various polymers that may be put in the water to aid in coagulation or flocculation can actually serve as foulants on an RO membrane, at least a spiral membrane. And this is a biofilm, kind of an illustration of a biofilm formation on a membrane surface. And keep in mind when we're talking about fouling, it isn't one or the other. It's always a combination of several of these effects. So it's an extremely complicated issue. There are some people that say that it is impossible to remove a fully formed biofilm from a membrane surface, as also a pipe wall, whatever, without literally physically removing it, scrubbing it. The oily wastes, these are a class of organic contaminants that are particularly important, particularly in hydraulic fracturing. By the way, I wrote a paper on that, so if you give me your card, I'll send you a paper on hydraulic fracturing. But the bottom line is none of these membranes can effectively handle free oil. Free oil will deposit on the surface of a membrane and give you endless problems. If the oil is emulsified, particularly if it's a chemical emulsion, it behaves as a particle, and a microfilter will remove it very effectively. If it's dissolved, and there aren't very many dissolved oils, but if it's a dissolved oil, that can effectively be removed by ultrafiltration, but not free oil. This is just an example of the type of the variety of fouling materials that may be found on a membrane surface. Possible solutions to fouling: pretreatment, which is basically remove the foulant before it gets to the membrane. Selection of the membrane device. I talked about the fact that MF and UF membranes, particularly in the plate and frame or the tubular construction, can be backwashed. That is a tremendous solution to fouling, at least remediation to fouling. And the system design. How do you design it to minimize this collection of fouling materials? These are the examples of the pretreatment that can be used to minimize the fouling of membranes. Again, you virtually never have just one fouling event. It's attributed to usually all four of these. The cleaning capability, which is basically associated with its ability to be backwashed. And as we said, the spiral wound cannot be backwashed if it's a salt-rejecting material such as reverse osmosis or nanofiltration. This is a busy slide, which is in the paper, but it kind of gives examples of the water source and what to do, how to treat this source to minimize the impact of these various classes of fouling materials. And then system design. The recovery in a membrane system, particularly in reverse osmosis, the primary design criteria that is within the purview of the designer is recovery. That percentage of the feed water that comes into the system that is pumped through the membrane and becomes permeate. That's up to the system designer. That's called recovery. And if you can actually generate this little formula based on mass balance equations. And the bottom line is if you have 50% recovery, which means that 1/2 of the water that comes into the system goes through the membrane and becomes permeate, you will double the concentration of whatever the contaminants are. It's just common sense when you think about it, because the movement, the performance of a membrane system, of all four of these membrane systems, is really the movement of water through the membrane. The contaminants are rejected and left behind. If you remove 50% of the water and it's contaminant-free, more or less, that means you've doubled the concentration of contaminants. So this is an exponential relationship. And this is why fouling is such a problem, because as you go up in this concentration factor from 50% to 80 to 90 to 95% recovery, you can see what happens to the concentration factor. And then quickly, disinfection. The ideal disinfectant has these properties, and it does not exist. Very early in the membrane industry, because we have such a problem disinfecting these thin film composite membranes, because they will not tolerate chlorine, they will not tolerate oxidizing agents. So the ideal disinfectant for them would be formaldehyde. Unfortunately, it's not ideal for the people that are handling it. So it is now basically outlawed. Formaldehyde is a reducing agent. It's the only effective reducing agent. Glutaraldehyde works fairly well. But basically, for membranes, for example, for disinfecting a membrane system, you have to use an oxidizing agent. And you are opening the door to all sorts of chemical attack when you do that. So the disinfectants that we see for disinfecting water supplies, chlorine compounds, including chloramines and chlorine dioxide, the other halogens, iodine, some bromine, and ozone. Ozone happens to be my favorite chemical disinfectant. Non-chemical, ultraviolet, or heat. That's just about our only choices. So, in conclusion, water is critical to life. Practices that we've been talking about for the last day and a half, conservation, collection, conversion, they're practical. There's lots of choices today. They're essential. And water recovery and reuse is an achievable goal. So, that's it. Thank you.